Sessions 12.1 One-Way Analysis of Variance. This session introduced the method of one-way analysis of variance, which is used for tests of hypothesis that three or more population means are all equal. So for these sessions, we are working on the hypothesis test and we only focus on the population means. And we want to test if all the population means are all equal to each other. We call that for the session 8.2, we have the population mean. At that time, we only have one population. So my null hypothesis, we're gonna test if the population mean is gonna be equal to a value. Session 9.2. We're still working on the hypothesis test for the population mean, but this time will be involve two population. So my null hypothesis, that will be population mean 1 equal to the population mean 2. For these sessions, 12.1, we're still working on the population mean, but this time we do have a 3 or more population. And for the null hypothesis, we want to test 3 or more population means are all equal to each other. You're gonna see I do have the K here. It depends on how many populations do you have. Because the calculations are very complicated, we emphasize the interpretation of the results obtained by using technology. So I will teach you guys how to use the formula to do the calculation, and after that we're going to use the TI-83 plus or TI-84 plus to take care of the calculation this part. Definition: one-way analysis of variance. You're going to see this is called ANOVA, okay, ANOVA. This means one-way analysis of variance. This is the method of testing the equality of 3 or more population means by analyzing the sample variance. So we need to calculate the sample variance, and then we're going to analysis of the variance to test if all the population means equal to each other. One-way analysis of variance is used with data categorized with one factor or one treatment, which is characteristic that allows us to distinguish the different population from one another. So we are working on the one-way analysis of variance. This is the session 12.1. For the next session, 12.2, we do have a two-way analysis of variance. Two-way means you will be under two factor or two treatment to analysis of variance to test if all the population means equal to each other. I will use the example to explain what is the meaning of one factor or one treatment. Now, let's look at the requirement. Populations have approximately normal distribution. So all the population is approximately normal distributions. Populations have the same variance. So we have a 3 or more populations, and for each populations, they do have the same variance, or they will have the same population standard deviation. The samples are simple random sample. Samples are independent of each other. Means for the population 1 is going to be independent of the population 2, independent of the population 3. They are not related to each other. The different samples are from populations that are characterized in only one way. Again, I will use the example to explain what is the meaning of one factor or one treatment. So look at this example. We are interested in students' study skills in a university. We are randomly select the students from this university. So this is what we want to do. We want to find out the students' study skills. So what we're gonna do, we're gonna select 5 people in the first year, 5 people in the second year, 5 people in the third year. And the students were given a study skills assessment, have a maximum score of 100. And we are interested in whether or not the difference exists somehow between the 3 different year levels. And we will conduct this analysis using ANOVA. So we are interested in the student study skills. So we have a different method to find it out. But for my example, I will select the samples in the first year, second year, and the third year. I will under only one treatment. The treatment is a year of the students. Okay, year of the students. So you're gonna see for my population 1, the year 1 students, I will give these 5 people a assessment test. And then this is the result. The student 1 got 80 points. Student 2, he or she got 90 points, and 85, 65, and 70. And this is my population 2, the year 2 students. And this is the result from their assessment test. Year 3, this is the population 3. And this is the result they got it from the assessment test in here. Okay, look at the notation. N represent all the data set have the same sample size. From our example, we are working on the 3 different populations. They will have the same sample size in here. You could word it like differently, but the calculation will be much more complicated. So I will let you guys only working on the data. They will have the same sample size for each populations. So here, my N, I could find out what is my sample size. For my population 1, I do have a 5 students. Population 2, I do have a 5 students also. Population 3, I also have the 5 students in here. Okay, K represent the number of data set. So means how many populations do we have? So we have 1, 2, 3. So my K, that will be equal to 3 in here. Okay, this notation means the variance of the sample means. Okay, variance of the sample means. So look at the sample means in here. Do you guys remember how to find out the sample mean? You could input this data on your L1 and then use the stat, the cal, and then one variable statistic to find out the sample mean, right? And also you could find out the sample variance as well. So you should get this data for the sample mean. Okay, add it all up divided by 5, or you just use the calculator. So what is the variance of the sample means? Means I have these 3 datas, and this is the sample means. I want to use these 3 datas to find out the variance. Okay, so you could plug in this data on your L4, just find out the variance, and you could see these numbers in here. I will show you guys how to use the calculator after this part. Last notation, the mean of the sample variance. Okay, mean of the sample variance. So I just asked you guys to input the data on L1, L2, and L3, right? So you should be able to find out the sample variance. This is what I get from my calculator. So what is the mean of the sample variance? This is my sample variance, and I want to find out the mean. So I want to add it up and then divide it by 3. You could get this number. And this is called the mean of the sample variance. Let me show you guys how to use the calculator. I have 3 populations, year 1, year 2, and year 3. And then I'm gonna plug in year 1 to my L1. So I'm gonna go on stat, number 1 added. So L1, that'll be 80, enter, 90, enter, 85, 65, and 70. L2, that'll be my year 2, so 80, after I input my 3 populations, I'm gonna click on the stat, go to the cal, number 1, one variable statistic. And then I want to see my data for my L1. So second one for L1, enter. So you can see I have a sample size n equal to 5. Sample mean, that will be equal to 78. Okay, 78. Now I want to find my sample variance. Sample variance means I want to take square with my sample standard deviation. So I recommend you guys write down this whole number. Okay, write down this number. Square of the sample standard deviation. So I'm gonna do 10.3682268 and then take square. Okay, you're gonna see I will square the whole thing in here. Don't take 1 or 2 decimal space. Try to take as many as you can. And then enter. So this is gonna be my sample variance. Okay, sample variance. So now I'm gonna write it down here, 107.5. Now I'm gonna find it out what is my sample mean and sample variance for my L2. So click on the stat, cal, second 2 for L2, enter. So I have n equal to 5, 80.2, that will be my sample mean. Again, sample variance, we're gonna take square of the sample standard deviation. Okay, you're gonna see 231.2, that will be my sample variance. Same idea for the L3 here. So 83, that will be the sample mean. Sample variance, we're gonna take square. So 6.3245532. Take square. You will have a 40 in here. Okay, 40. After I find the sample mean and sample variance, we want to find out what is the variance of the sample mean. Variance of the sample means, it means that I need to input this one to my L4. So I'm gonna click on the stat, go to number 1 added, and now I'm gonna choose number 4 here. So I'm gonna do 78. Okay, L4, that'll be my sample mean. Go to the stat, cal, number 1, and second 4 for L4. Okay, variance of these 3 data. So again, I'm gonna take the square with my sample standard deviation. So 2 take square. You will find that's a 6.28. This is going to be the variance of the sample mean. And then for the mean of the sample variance, so you want to find the mean with these 3 data. Either you can put it into your L5. Go to the stat, cal, second 5 for L5. You will see the sample mean, that will be 126.23. Or you could just add up these 3 numbers divided by 3, you're gonna get the same answer. So this is how you guys use your calculator, find out all the details with the sample mean, sample variance, variance of the sample mean, and mean of the sample variance. Okay, this is the instruction how you guys use the calculator to find all the details. I'm gonna show you guys how to use this calculator after the first example. Okay, procedure to perform the one-way ANOVA test. We will be using the F distribution. Remember the F distribution? We talked about this on the session 9.4. Okay, session 9.4. So first, figure out what is your sample size and what is a K. K means how many populations do you have. So for my previous example, we have a free set of the data, so K will be equal to 3. And then find out the degree of freedom of numerator and degree of freedom of denominator. Okay, degree of freedom of numerator, just K minus 1. Degree of freedom of denominator, you want to do N minus 1 and then times with the K. And also highlight these two guys. Make sure for this session, you need to figure out these two guys in here. The variance of the sample mean and mean of the sample variance. Original claim either has null hypothesis or alternate hypothesis. Okay, for the null hypothesis, for these sessions, we want to test the hypothesis of the population means are all equal to each other. So this is always equal. And then you could see the K in here. It depends on how many populations do you have. And for the alternate hypothesis, don't put not equal to, okay? Some students put like mean 1 not equal to mean 2, not mean 2, mean 3, okay? This is wrong. Write it down. At least one of the means is different from the others, okay? So we want to prove if they are equal to each other or at least one of the mean is going to be different. Test statistic. So you're going to use these two guys, multiplied by the n, divided by here, okay? So this is the test statistic formula. Distribution, this is always whitetail test, okay? For the session 12.1 is always whitetail. So after you find your test statistic from the step 4, use the F here, find out the p-value, okay? That will be the FCDF. Test statistic to 1v99. Degree of freedom of numerator, degree of freedom of denominator. Conclusion, compare with your significance level to see reject or fail to reject. Final conclusion is going to be from the session 8.1, the 1, 2, 3, 4 conclusion. Example 1. Simple random samples of cheap weights after treatments with nothing, fertilizer, irrigation, or both are listed below. The samples were independent and taken from normally distributed populations with the same variance. Use the p-value method and a 5% significance level to test the claim that the treatment samples come from the populations with the same mean weight. Okay, so you can see we have like more than 2 populations. We have 1, 2, 3, and 4. Okay, so this is the first set of the data for the nothing, fertilizer, irrigation, and then both. So we have 4 populations. First, I want you guys to figure out what is the sample size. How many data do you have for each population? We have 1, 2, 3, 4, 5, right? So n equal to 5 in here. Same idea for these 3. Okay, what is your n equal to? What is your k equal to? N will be your sample size, right? And how about the k? How many populations do you have? You have 1, 2, 3, 4. Okay, so k equal to 4. And then figure out what is the degree of freedom of numerator, degree of freedom of denominator. Okay, plug it in. K minus 1, that will be equal to 3. N minus 1, that will be 5 minus 1, which is 4. 4 times 4, 16. Now use your calculator. Plug in your data on L1, L2, L3, and L4. Figure out what is the sample mean and sample variance. Okay, now I'm gonna plug in L1 for my nothing. Okay, so my k equal to 4, I should have a 4 set of the data, okay? 1, 2, 3, 4. It's equal to 1, 2, 3, 4. Now I'm gonna find out my sample mean and the sample variance. So go to the stat, cal, number 1, second one for L1. So I got my sample mean equal to 1.19. Sample variance, I'm gonna take square with this picture. Okay, so go back here. This is 1.19. That will be my sample mean. Sample variance. Okay, you're gonna get 0.39155. Okay, and then check your work for the L2, L3, and L4. Find out the variance also. Okay, now I want to find out my variance of the sample mean. So I'm gonna click on the stat, number 1 added. This time I'm gonna go to L5. And then I'm gonna plug in the sample variance on my L6 also. Okay, go to the stat, cal, number 1, L5, enter. So find the variance of the sample mean. We're gonna take square of the sample standard deviation. Okay, you're gonna see that's a 0.205. That will be the variance of the sample mean. Now find out the mean of the sample variance. So click on the stat, cal, number 1, second 6 for L6. So the mean of the sample variance, that will be 0.2766825. Okay, so write it down on your number 1 here, okay, or you could just put it in here. Now, original claim, so the claim statement here. Tester claimed that the treatment samples come from the populations with the same mean weight, okay, they are equal to each other. And then we have 4 populations. So I'm gonna write it down with the mean with the N, represent the first one for the nothing. The mean of F, that'll be the fertilizer, and then mean of irrigation, and the mean of the both. So no hypothesis, alternate hypothesis. At least one of the means is different. Okay, test statistic. So plug in the number, you know the N, you know the variance of the sample mean, you know the mean of the sample variance. Plug it in, show me your work. You should get this guy. This is the test statistic. Okay, distribution. F distribution is skewed to the right, and we are always working on the right tail. So this is my test statistic. Use the test statistic to find the p-value. So we're gonna use FCDF test statistic to 1E99. And then 2 more numbers. degree of freedom of numerator, degree of freedom of denominator. Use the calculator, you should get 0.034. Now compare with your significance level. Okay, less than, so it's going to be reject. And then conclusion, original claim go to the null hypothesis, and we have the reject, so that will be the number one conclusion. Okay, so this is the hypothesis for the ANOVA. Now, let's use the calculator to check your work. So we already have my data, L1, L2, L3, and L4, okay? We only have a 4 population, so we have L1 to L4. L5 and L6, this is how we finding the variance of the sample mean and the mean of the sample variance. So we're gonna go to the stat, go to the test, go to ANOVA here. We have a k equal to 4. So second 1, comma, second 2, comma, second 3, comma, last one, second 4. Okay, ANOVA from L1 to L4. Enter. Okay, you're gonna see the first number here, the F. This is gonna be your test statistic, 3.7046. And then the P here, this is talking about the P value. Okay, let me show you guys the P value. 0.034, okay, 0.034. You also see there's a factor, there's a degree of freedom. Under the factor, the degree of freedom equal to 3, this is talking about the degree of freedom of numerator, okay, numerator. And then, degree of freedom equal to 16, this is under the error. This is talking about the degree of freedom of denominator. Okay, let me capture this screen and explain to you guys one by one here. Okay, this is how we got it from my calculator. One more time. First one, F. This is talking about the test statistic, the F. Second one, this is your P value. Under the factor, the degree of freedom, that will be the numerator. Under the error, the degree of freedom, that will be the degree of freedom of denominator. One more here, under the error, the MS, this is talking about the mean of the sample variance. Okay, the mean of the sample variance. That's one more here. Under the factor, the MS, this guy, 1.025, this is the N, the sample size, times the variance of the sample mean. Okay, N times the variance of the sample mean. So let me take out this one here. N times variance of the sample mean equal to this number. And then if I do the math, I divide it by N for both sides. So this is how we figure out the variance of the sample mean. So my N here, sample size, that will be equal to 5, right? So divided by 5. You're gonna get variance of the sample mean, that's a 0.205. It matched the data from here. Okay? And actually, for the homework and the exam, you could just use your calculator. I will still show you guys this part on the exam and the homework. That's up to you guys if you want to fill it in. Either you use the calculation, just what we did, finding out sample mean, sample variance, and find out the variance of the sample mean, mean of the sample variance, step by step, or you could just use your calculator, figure out all this information, degree of freedom of numerator, denominator, and also these two guys. Okay, this table here, this is optional. It's up to you guys if you want to formula or use the calculator directly. But for the test statistic, you need to show me the formula. Same idea with the p-value. You need to show me all your work here. Okay? So you may want to write it down this part on your notes. Make sure you know how to check your work, or you could use your calculator to get this information directly. Okay, last example. And this example will use the critical value method. So when you guys try to do it by yourself, either using the table here step by step, or you could just use your calculator. Let's do it together. The chest deceleration measurements in gram, where gram is the force of gravity, from samples of small, mid-size, and large cars. Assume that we plan to use a 0.05 significance level to test the claim that the different size categories have the same mean chest deceleration in the standard crash test. So we have the first data, 1, 2, 3, okay, small, mid-size, and also the large. So what is the sample size in here? 1, 2, 3, 4, 5, 6, 7. Okay, and you go to 7. How about the K? How many populations do you have? We have 1, 2, 3. So K equal to 3. Figure out degree of freedom of numerator, degree of freedom of denominator. You should get 2 and 18. Okay, either you use the table here, use the calculator, find it out, this, or you could just use the calculator directly, find out the variance of the sample mean and the mean of the sample variance. Okay, you should get these two guys. Make sure highlight this one. I need to see these two guys on the homework and also the final exam. Okay, original claim. Test the claim that the different size categories have the same mean weight. Okay, they're gonna equal to each other. So I have a mean of the small equal to the mean of the mid-size equal to the mean of large. No and alternate hypothesis. No hypothesis is always equal. Alternate hypothesis, at least one of the means is different. And this is always whitetail test. Okay, distribution. We are working on critical value method. So area of the whitetail, that will be equal to your significance level, which is going to be 0.05. Now, figure out the critical value. Write it down the degree of freedom of numerator and the degree of freedom of denominator. Okay, look at the F distribution. You can see the F distribution, you do have two pages. The first page here, this is the F table for significance level 0.025. Second page, that's a significance level equal to 0.05. Our significance level is 0.05, so make sure you look at the correct one. Look at the 0.05 on the whitetail. And then the degree of freedom of numerator is going to be equal to 2. So we're going to look at this 2 column. Degree of freedom of denominator, that will be equal to 18. So 18 and 2. This is going to be your critical value. 3.5546. Okay? If you can't find the exact degree of freedom, you could find the closest one. For example, let's say I have 32, okay, 32 and 2. So I don't have the 32 here. I will try to look for the closest one. So that will be 30, okay? Write it down. This is going to be your critical value. And solve it on the distribution here, okay? This point, that will be equal to your critical value. Now, find the test statistic. Plug in the numbers from the step 1 you should get 3.288. And then make sure critical value method show me where is your test statistic located. So 3.288 somewhere like here. Draw the conclusion based on the critical value method. Okay, don't try to find the p-value and use the p-value method. I want you guys to use the critical value method. So the test statistic is not in the critical region. This is the critical region, right? So this is not in the critical region. So we have failed to reject. Conclusion, that will be the number 2 conclusion. That is not sufficient evidence to warrant rejection of the claim. Make sure give me the complete sentence. Okay, so this is how we using the critical value method to perform the hypothesis testing of ANOVA. That's it, session 12.1.